Imagine trying to send a flawless, uncompressed 4K video signal from a control room across a sprawling casino to a sports bar 20 miles away.
Yeah, I mean, if you use standard copper cables, your signal just dies before it even leaves the building.
Exactly. So welcome to the deep dive. Today our mission is decoding this incredibly dense product page for the Kramer 676T transmitter. We are looking at the invisible technology powering all those massive visual displays you see everywhere.
It's a really fascinating piece of tech.
Okay, let's unpack this. How do you actually bridge a 20-mile gap without losing a single pixel?
Well, you do it by abandoning electricity completely. You turn that data into light.
Right.
Because pushing modern video over copper wire it's like trying to shout complex instructions across a crowded, noisy stadium. The signal degrades, and interference just drowns it out.
Which makes fiber optics more like, using a perfectly focused laser pointer in the pitch dark.
Exactly. It doesn't scatter, it doesn't experience interference, so it can travel infinitely further, instantly.
Which makes total sense when you look at the sheer volume of data this Kramer unit handles. I mean, it takes standard HDMI video plus RS-232.
Which are just basic command signals.
Right, for turning equipment on and off.
Right.
And it translates all of that into an optical signal pushing 18 gigabits per second.
What's fascinating here is why it needs that massive 18 gigabit highway. It pushes a maximum resolution of 4K at 60 hertz with full 4.4.4 color space.
And that 4.4.4 metric means there is absolutely zero color compression, right?
Yeah, exactly. Every single pixel on the screen gets its own dedicated color data. That creates this astronomically high bandwidth requirement that copper simply chokes on.
Wow.
By instantly translating those heavy electrical impulses into light, you achieve that near zero latency video conversion.
Here's where it gets really interesting. By translating it to light to solve the bandwidth problem, you accidentally unlock a massive secondary benefit.
Extreme distance.
Right. The specs show that if you use a multi-mode fiber setup, the signal reaches about 1.8 miles.
Which is already a huge distance.
It is. But if you swap to a single-mode fiber, which uses a narrower, much more focused beam of light, it hits a staggering 20.5 miles.
It's wild.
And when you hear 20 miles, your first thought is probably, well, I don't have a living room that big. Why do I care?
Right. I mean, this isn't for home theaters. This is the invisible backbone of modern infrastructure.
So why 20 miles?
The reason for this range really comes down to a feature called multi-drop signal distribution. Imagine wiring that sprawling casino. With standard copper cables, every time you want to split a video feed to multiple TVs, you have to install a bulky, powered distribution amplifier.
Just to replicate and boost the electrical signal.
Exactly. But with fiber, because you're dealing with light, you don't need a powered machine to replicate the signal.
Wait, so you could just physically split the beam?
Precisely. Installers can use optical splitters, they're essentially specialized prisms, to take one single beam of light and physically fracture it out to multiple receivers simultaneously.
Oh, that's incredibly smart.
Yeah, there is no added latency, and it requires no external power at the splitters. It's just pure physics doing the heavy lifting over vast distances.
Okay, I am looking at the $820 price tag for one of these transmitters.
Yeah.
And my first thought is, the hardware is only half the cost.
Oh, for sure.
The real nightmare has to be paying an IT team to manage a 20-mile network. If you have perfectly synced screens spread across a massive venue, doesn't a system this expansive become a maintenance black hole the second a TV gets unplugged?
Well, you would naturally assume that, but the engineering specifically counters that complexity. It features something called IEE Pro.
Okay, what is that?
Usually when you plug a monitor into a video source, they perform a digital handshake. If the monitor drops offline, the source panics and cuts the feed.
Which would take down everything.
Right. So IED Pro essentially memorizes the exact display requirements of the monitor and fakes that handshake with the video source.
Oh, wow. So even if a display 20 miles away is temporarily turned off, the central video feed never crashes.
Exactly. It's maintaining the illusion of a perfect connection to keep the whole network stable.
That is brilliant. And I see it uses CEC, which basically means it manages its own power automatically, shutting down displays when they aren't in use and waking them up when a presentation starts.
Yeah. If we connect this to the bigger picture, it is all about reducing friction. The hardware itself is incredibly dense. It uses a fanless enclosure.
And you can fit 3 of these units side by side in a single 1U rack space, right?
Yep, meaning they take up just one standard horizontal slot in the server rack. Add in the simple LED status lights on the front for instant local troubleshooting of power and fiber links. and managing miles of infrastructure becomes surprisingly simple.
So what does this all mean? It proves that high-end AV distribution is fundamentally about turning massive, overwhelming data into manageable, lag-free light.
Excellent.
The next time you're sitting at a massive sports bar or a concert venue, watching perfectly synced screens spread across the entire building, consider the invisible beams of light running miles beneath your feet to make it all possible. What other massive optical networks are silently shaping the world you look at every day?